Hello everybody! Welcome to video 7 for module 2. This is the last video in the module. I might have just said that in the last video, and if so, I apologize for psyching you out like that. This is future me coming back after I finished filming everything for the course and realizing that I need this video and that it needs to go here. So what's it about? It's about confidence intervals for proportions. And so before talking about how to do this, let's just set it up with an example. So in a certain country, there is a national election coming up, and there are two candidates, candidate A and candidate B. And I want to know the true proportion of people in the country who prefer candidate A. So I took a random sample of 500 individuals, and I polled them, and I found that 320 of them like candidate A. So we have a sample proportion, 320 over 500, which is exactly 64% of the population. So that's what we're seeing in our sample. But what does it say about the larger population? I want to do a hypothesis test on P, where P is the true proportion for the entire country. So I'm going to set up two hypotheses like this. I've got P less than or equal to 0.65 and P greater than 0.65. And where do these come from? I made them up, so I don't really have a good argument for you about this should be the null hypothesis and this should be the alternative. I just made them up for an example. And our sample proportion is 0.64, which looks like it's falling in the null hypothesis range. But the next sample will have a different sample proportion. And depending on how variable those numbers are, we're going to maybe not fall in the null hypothesis range sometimes. And so I'm not really sure if for the entire population, just by looking at a sample proportion of 0.64, I'm not really sure which one of these is right, where P is the proportion for the entire population. So just to put something concrete in here, I'm going to use a level of significance or size or alpha of 0.10. And so again, we have an estimate, 16 over 25, which is exactly 64%. And this is a hypothesis test about a proportion using a sample proportion. And up until now, we've done, I think, exclusively sample means. And there's nothing new here because a sample proportion is a sample mean if you look at the sample the right way. So I'm going to go through my group of 500 people and I'm going to figure out who voted or who preferred candidate A and who preferred candidate B. And for everyone that said they preferred candidate A, I'm going to label that person with a 1. And everyone that said they preferred candidate B, I'm going to label that person with a 0. So if I go add up all of those zeros and ones, the total is going to be the total number of ones. That's going to be the total number of people who preferred candidate A. And so if I divide by 500, that gives me the proportion. In other words, the sample proportion of people who like candidate A is the sample mean if you're starting with a random sample x1 through x500 from the Bernoulli distribution, which takes on the values 1 and 0, and they're 1 with some probability p, and 0 with the rest of the probability. So it's as easy as that. The sample proportion is a sample mean when you set up the model the right way, and we already know how to compute hypothesis tests for means of distributions. Now, we do not have a normal distribution here, far from it. We've got zeros and ones. We have a discrete distribution that only takes on 2 values. By the central limit theorem, we should be okay, though, with a large sample. Now, we talked about large being n greater than 30 or possibly greater than 40. In this course, I'm never going to try to trick you by giving you a 35. I'm going to make sure it's large. However, those rules of thumb are for unknown distributions. They are like catch-alls that are supposedly going to tell you when your sample mean gets close to normal for a generic underlying distribution, which is kind of a hard task. In this case, we know the underlying distribution is Bernoulli, So I might be able to tell you something more specific about what sample size we should use in order to use this normality assumption, and that will be coming up in a little bit. So once again, p hat is going to be the number in the sample that like candidate A over the total sample size, and this is an x bar when I have Bernoulli random variables representing the preference of each voter. So we're going to say by the central limit theorem that this p hat, because it's an x bar, gets normal for a large enough sample. And before we do that, let's specify the mean and variance. So the expected value of x bar is the expected value of any one of the x's. That's how x bars or sample means work. And for the Bernoulli distribution, that mean is p. The variance for our estimator, the variance for p hat, or equivalently x bar, is the variance for any one in the sample divided by n. Remember, we're used to seeing sigma squared over n, and the sigma squared is the variance for one of them, and in the Bernoulli case, that is p times 1 minus p. So, by the central limit theorem, we're saying that our p hat is approximately normally distributed, and the mean and variance are whatever the mean and variance are. We just figured them out here. So, by the central limit theorem, p hat is approximately normally distributed with mean p and variance p times 1 minus p divided by n. Now, in particular, this means that if we standardize it, we take p hat and we subtract its mean and divide by its standard deviation, or its square root of its variance, like this, that this is going to behave roughly like a normal 0, 1 random variable as the sample size gets large. So what does large mean? I already told you in this video, I recapped the rule of thumb that n greater than 30 or 40 is generally considered large enough to use the central limit theorem. But that is a rule of thumb that is devised with an unknown underlying distribution. In this case, we know the underlying distribution. It's a Bernoulli distribution. And we might be able to do a little better or worse, or at least something more specific to this distribution. So if you want to say n is greater than 30, go for it. But that will actually be problematic if the true p is really, really, really small. Like if the true proportion of people who like candidate A was 0.0001, then with a random sample of size 35, you might never see someone who preferred candidate A. So it really should depend not only on the sample size, but the true value of the parameter p, which of course is unknown. But it lives between 0 and 1, and so does its estimator. And the normal distribution lives between minus infinity and infinity. And yet the statistic will only take on values between 0 and 1. So it seems a little crazy to model it with a normal distribution, but we can if we take our sample size large enough so that that normal distribution gets really, really narrow and squished, and almost all of it is between 0 and 1. So it is common knowledge and something you can find using the function p norm in R. You can figure out that approximately 99.7% of the area under the standard normal curve lives between minus 3 and 3. And the standard normal curve has variance and equivalently standard deviation 1. So this is saying over 99% of the normal distribution is within 3 standard deviations of its mean. In our case, our estimator is p hat, and it has a standard deviation, which is given by the square root of p times 1 minus p over n. And so if we look at our estimator and subtract 3 standard deviations and add 3 standard deviations, hopefully we can get that entirely contained within the interval 0 to 1. Now you'll notice that the standard deviation was the square root of p times 1 minus p over n, and it didn't have hats in it, but I don't know what p is, so we're going to try to put in the estimator, which is commonly done. So on the previous slide, I had square root of p, 1 minus p over n, and now I have square root of p hat, 1 minus p hat over n, to try to at least guess at the standard deviation to try to at least guess at when the normal 0, 1 distribution is appropriate, to describe when the normal, or to guess at when the normal distribution is appropriate for modeling p hat, which only takes on values between 0 and 1. So this is going to say more than 99% of this normal distribution is between 0 and 1. And if this interval is contained in the interval from 0 to 1. Okay, so as usual, I've summarized the hypotheses up here just so you can keep them in mind. Step 1 is to choose a statistic. So this is a test about a proportion, and we're going to choose the sample proportion. Oftentimes, this statistic is a common sense estimator of the parameter in the null hypothesis. But we'll eventually see in this course that it doesn't have to be something that you would consider an estimator, just a statistic that you can work with. And I talked a little bit about this already. No, I didn't. I'm future me. So eventually, I will talk more about choosing the statistic for step 1. In all the hypothesis tests right now, I'm going to give you the statistic for step 1. Step 2 is to come up with the form of the test. This is when you look at the statistic and remember, you assume the null hypothesis is true, but you're going to go with the alternative hypothesis if it being true is reflected in your statistic. So the alternate hypothesis says that p is larger than 0.65, as opposed to the smaller values that are in the null hypothesis. And so if we believe that's true, that's going to come out in the data as p hat being large. And so the form of the test is going to be to reject the null hypothesis in favor of the alternative if p hat is above some value c to be determined. Step 3, we want to use alpha to find the value of c, and here's where we need to assume that at least approximate normality of p hat. So these were the two rules I gave to you before, either n greater than 30 or something more specific to the Bernoulli distribution. And I went and computed this for our candidate A, candidate B example, and these two numbers came out to be 0.5756 and 0.7044, which is fully contained in the interval from 0 to 1. So I have a check mark. We're good to go, assuming normality, approximately. So still in step 3, we haven't done it yet. I just made an argument for normality. In step 3, we have to find c, and this is where alpha comes in. Now, alpha is the maximum probability of making a type 1 error. Before I say what that maximum's over, remember, a type 1 error means you reject the null hypothesis, but you shouldn't because it's true. So the type 1 error means we reject the null hypothesis when the true parameter is p, and right now this is just a variable, but then I'm going to maximize it over all the p's in the null hypothesis region. More specifically, I'm going to maximize over all the p's less than or equal to 0.65. Next step, we're working with a normal, is to standardize it. Subtract its mean, divide by its standard deviation. So the mean or expected value for p hat is p. The standard deviation is the square root of p times 1 minus p over n. And we're assuming the true parameter is p. That's the p out here after the semicolon. So subtract p, divide by the square root of p, 1 minus p over n. Do the same thing to both sides. And then the thing on the left we're going to call z, and where z is a normal 0, 1 or standard normal random variable. And I put approximately here because this is all kind of approximate and based on the central limit theorem. So if you go onto YouTube or something, or wherever you're looking for hints about hypothesis testing, they likely won't have this maximum here. They will just say to compute this probability with p naught, the null hypothesis value, in this case 0.65, plugged in. But we know better. They're not wrong, but why do they do that? we want to control the worst case scenario, the maximum probability of making a type 1 error. So we want to maximize this probability over all the p's between 0 and 0.65. And this is a really difficult thing to work with. The denominator alone is, if you graph it as a function of p, is a parabola in p. So it goes up and then it goes down. It's not increasing or decreasing. It has its moments, right? And then that's the denominator under c minus p. So this whole quantity here, it's hard to figure out what it's doing. So you can use your calculus and take some derivatives, and you will find that this whole quantity is in fact decreasing. But I think that's really hard to do. Those are hard derivatives to set equal to 0 and solve. So what I'm going to do is I'm going to graph this quantity right here as a function of p. I'm just going to plug in points. I'm going to take p's from 0 to 1, very finely meshed. 0, 0.001, 0.002, all the way on up to 1, and I'm going to compute this. Except I don't have a c, so what c's make sense here? Remember, our rejection rule is to reject if our p hat is greater than c, which we're still trying to find. Now, p hat is a sample proportion. It's the proportion of people in the sample who liked candidate A. So it's not going to make sense to have c's greater than 1, because you will never reject the null hypothesis then, which might sound good to you, but you know we can't do that because there will be error and we'll never be able to get that probability equal to the 0.10 or the alpha we want if that probability is always 1. So I'm going to consider just c's between 0 and 1 and graph this. So what I have here are graphs in p, and the bottom one has c equals 0.1, and the next one up has c equals 0.2. On up, the top one has c equals 0.9. But you can see that these are all decreasing functions of p. And in fact, if c gets above 1, it's no longer as clear. So I think this is why people on YouTube videos tend to skip this part and not talk about the maximization at all. It's pretty ugly. But going back to this, we have seen, sort of convinced ourselves with a lot of evidence, that this quantity over here is a decreasing function of p. So the probability that a standard normal is greater than a number, and then greater than a lower number, that probability is going up. For example, the probability z is greater than 0.2 is whatever it is. For z to be greater than 0.1, a lower number is going to be higher because it's easier to be greater than 0.1 than it is 0.2. So that tells me that while this is decreasing, this entire probability is increasing as a function of p. So if I want to maximize it over all the p's between 0 and 0.65, I'm just going to plug in the 0.65, the right endpoint of that interval. Okay, so I have plugged it in, and this whole probability was supposed to be 0.10. And so what number is the standard normal above with probability 0.10? That is how we define our critical value, lowercase z sub 0.10, which means this whole thing in here has to equal lowercase z sub 0.10. So from this, I can solve for c, and I can give the rejection rule. I forgot to put step 4 on this slide, but this is step 4, where you bring it on home. Our rejection, or the form of our test, was to reject the null hypothesis if p hat was greater than c. We just figured out what c needs to be. So now we can say reject the null hypothesis if p hat is greater than all of this stuff. So let's try it for our actual example. In our example, we had a sample of size 500. We talked to 500 people and polled them about their candidate preference. And in that sample, we saw 300 and something, which came to 16 out of 25, which came to 0.64, was the proportion of people in that sample who preferred candidate A. Our alpha is 0.10, and z sub alpha you can get from R. This is the number that cuts off area 0.10 in the upper right tail of the standard normal distribution, And to get that, you have to type Q norm of 0.90 because the R function Q norm actually takes the lower area probabilities, the area on the left side of the cutoff. And so doing that in R, I got 1.28. And down here is what I had on the previous slide. This was the right thing. So on the previous slide, I said reject if p hat is greater than a thing. And this is that thing. It comes out to 0.6773. And so our p hat was 0.64, and this is not greater than 0.6773. And so we're not in the rejection region, so we fail to reject the null hypothesis in favor of the alternative at 0.10 level of significance. And the bring it on home is go back to the context of the problem. The data here does not suggest that the true parameter P, the true proportion of the overall country population that prefers candidate A, it does not suggest that that's greater than 0.65. So we're going to stick with the null hypothesis that that true proportion is less than or equal to 0.65. Okay, so this concludes Module 2, seriously this time. In the next module, we're going to start chipping away at the assumptions that have been plaguing us so far. I feel like I said that in the last video. I don't have a script, but that's just what comes into my mind, plaguing. So we had to assume, at least when doing a hypothesis test for the mean, that we had a normal distribution or a large sample, so we can use the central limit theorem, and that the variance, sigma squared, is known. And we're going to take those away in the next module. So you probably have a quiz or a lab to do at this point, but when you're done, I will see you in the next one.
Once upon a time, there was a statistics professor who made a great number of videos that had terrible sound quality. She tried microphone after microphone, but nothing seemed to help. There were breathing noises and animal noises and an echo off the walls like you wouldn't believe. Her S's hissed and lingered, and she was very sad. Then one day she found a new microphone that sounded pretty good. She was so happy to find it that she decided to re-record hours and hours of videos. She was so determined to finish and to not fall back on the existing videos that she banished them to the recycle bin and emptied it. When she finished her long journey, she was horrified to realize that the jack on the new microphone was not secure. She had no audio. But wait, all was not lost. The camera had a built-in microphone that was horrible and tinny, but she used it nonetheless, and she was sad.